When something like ChatGPT just bursts onto the scene, it feels like actual magic, right? Answering any question, writing poetry, spitting out code. How does it actually work? Well, it turns out it's not magic at all. It's engineering, and it's built on principles that we can really wrap our heads around. There's this great principle, supposedly from the brilliant physicist Richard Feynman, and it is the absolute key to understanding modern AI. To really get how this stuff works, you gotta pop the hood and see how the engine is built.
And, well, that's pretty much the whole idea behind Sebastian Raschke's book, Build a Large Language Model from Scratch. He gives us the complete blueprint. So what we're going to do right now is take that blueprint and actually walk through it. Let's see what's really inside that so-called black box.
All right, so let's get into the weeds. What are the real, concrete steps you'd have to take to build one of these things from the ground up? We're going to walk through this conceptual construction project one step at a time.
Okay, so any big construction job, you got to start with a foundation, right? For a large language model, that foundation is all about learning to read. And for a computer, reading isn't about understanding words like we do. It's about turning our messy, beautiful human language into cold, hard numbers that it can actually work with.
And what's so cool is how simple this starts out. You take a sentence, right? Hello world. First, you chop it up into these little pieces we call tokens. Then you basically build a dictionary, a vocabulary, and give each unique token its own ID number. So hello becomes 7, world is 1, and bam, the computer isn't seeing words anymore, it's seeing a string of numbers.
So that whole process is called tokenization. And look, our little example here is super simple. But the big models, they use way more advanced methods to build their vocabulary. Because you have to ask what happens when the model sees a word it's never, ever seen before?
Well, that's where this clever trick comes in called byte pair encoding, or BPE for short. It's a really smart way to handle any word you throw at it. It can see a new word like playfully and break it down into smaller parts it does know, like play and fully. It basically means no word is ever truly a stranger.
Okay, so we've got our foundation. The model can read numbers. That's a huge first step. But language isn't just a list of words. It's about context, right? Now we have to build the engine, the part that actually understands that context. And this is the revolutionary component at the very heart of the transformer architecture that powers all of these modern models.
But to really appreciate how big of a deal this was, you have to look at what came before. Older models, these things called RNNs, had a terrible memory problem. It's like they'd read a really long sentence, and by the time they got to the end, they'd completely forgotten what the beginning was about. The signal for learning just faded away.
And then came the big breakthrough, the attention mechanism. This was a total game changer. Instead of processing words one by one in a line, it lets the model look at the entire sentence, all at once. For any single word, it can literally pay attention to all the others and figure out which ones are the most important for understanding its meaning.
And the secret sauce that makes this work is something called skip connections. Just like the quote says, they're like little information highways that let that learning signal bypass all the traffic. It's how a model can read a huge paragraph and know that the word it at the very end is talking about the cat from the very first sentence. That memory problem? Poof, solved. All right, we've got the blueprints, we've got the engine, but how does this thing actually get smart? The learning process itself is, and this might surprise you, incredibly simple at its core. It's all about one thing: predicting the next word. This first giant learning phase is called pre-training. And what that means is we basically just set the model loose on a ridiculously huge chunk of the internet. We're talking vast amounts of text, and it just starts absorbing everything: grammar, facts, how to reason, all the patterns hidden in all that data. And how does it learn? It just gives itself millions and millions of little quizzes. It takes a piece of text, like a little window that slides along, and its only goal, its entire purpose in life at this stage, is to guess the very next word that comes after that window, over and over and over.
And when it first starts out, oh boy, it is terrible. I mean, look at this example from the book. The output is just total, random nonsense. It has no clue what it's doing yet.
So obviously we need a way to measure how wrong it is. And we do that with something called a loss score. It's just a number, a single number that tells us how far off the model's guess was from the right answer. High number, you're way off. Low number, you're getting warmer.
And this is the key. This is the whole point. That entire, hugely expensive, multi-million-dollar training process
It all boils down to one simple goal: adjust the model's billions of internal settings over and over and over again to make that one loss score number as tiny as possible. That's it. That's the game.
So, after all that pre-training, what you have is this incredibly smart model. I like to think of it like a brilliant college grad. It knows a ton about a ton of different things, but now it needs a job. And that's where fine-tuning comes in.
Yeah, this table really nails the difference. Pre-training is the huge, expensive, learn everything phase. Fine-tuning is the small, cheap, get good at one specific thing phase. We're not teaching it English again, we're just showing it how to apply what it already knows to a new task.
So, for example, you could take that massive model and just show it a few thousand text messages with each one labeled either spam or not spam. And in almost no time, it'll become a super accurate spam detector. It just adapts all that general knowledge to this one tiny task.
Or, and this is where it gets really cool, you can do what's called instruction fine-tuning. This is the magic step that turns a simple text predictor into something like ChatGPT. You basically show it a bunch of questions and really good answers, and you teach it how to be a helpful conversational assistant. And that's the whole blueprint, right there. Those are the major stages. You prep the data by turning words into tokens. You build the architecture, that transformer with the powerful attention mechanism. You pre-train it on a staggering amount of text so it learns language. Then you fine-tune it to give it a specific job. And that last step you see, inference, that's just the fancy word for actually using the model. You give it a prompt, and it generates an answer. The machine is built.
So when you see all the pieces laid out like that, it's not really a magic black box anymore, is it? It's this incredible, complex, but ultimately understandable piece of engineering. Knowing that blueprint, from the simple token all the way to fine-tuning, it kind of pulls back the curtain. So the real question is, now that you know how it's built, does that change how you think about the